The purpose of this video is to look at the connection between calculus and physics, in particular looking at the position of a particle, the velocity of a particle, the speed of a particle, and the acceleration of the particle, and most importantly to learn that without calculus there would be no physics. So let's begin by looking at some ideas that hopefully you recall and learned when you were in middle school. So let's just kind of walk through these notes. I'm going to add some annotations and you can add them into your notes as you pay close attention and you are an aggressive learner as you're watching this video. So we begin. A position function, s of t. So the first thing I'd like for you to note is that a lot of times in calculus we will use s of t as a position function. A position literally tells you the position of the particle. Where is the particle in time? It is a linear measure, so it would be measured in feet, inches, miles, meters, etc. In calculus, most things are measured in feet per minute, feet per second. It's the position of a body or a particle at a given instant of time, where time is measured in seconds or minutes or hours. The position of a free-falling object. So this is something you looked at when you were in Algebra 2. If you throw an object into the air, its pathway will form a parabolic path. And so an object with no other forces acting on it other than gravity, position function is negative 16t squared plus v sub 0, where v sub 0 is the initial velocity. How hard did you throw the object, or how fast is it going at takeoff? The initial position, how high is the object in the air? And so that's a function that you will need to know. And now let's go back to middle school. When you were in middle school, hopefully you learned that distance is equal to rate times time. In other words, if you want to know how far you travel, if you know how fast you were traveling and how long you were traveling, you multiply, and that will tell you how far you traveled. Therefore, how fast you travel, the rate, is equal to distance divided by time. In other words, if d is equal to r times t, distance is equal to rate times time, then obviously the rate at which you travel is distance divided by time. Now we're going to talk about the d word of distance because there are two words that we use in physics that are not exactly the same. The first word is distance, the other word is displacement. We'll talk more about that on another slide. All right, so we started out with position. This is what you can think of as the original function. Now, if I want to know how fast the object is moving, I'm going to change colors here. Now we're talking about the velocity of the particle. Now, something that, again, I'll talk about on another slide, velocity has two measures. It indicates the direction a particle is moving, according to the sign, positive or negative, and how fast the particle is moving. So if we want to know the average, here we go with Algebra 1 again, the average rate of change of position, the literal definition of average rate of change is delta S over delta T, which is change in position over change in time. Here are the words that indicate that. And so if position is measured, for example, in feet, notice the numerator units are feet, and we're dividing by time, and so that's literally how you determine the units. The numerator units are feet, the denominator units are time. Average rate of change, since it's an average, we're going to need 2 points to determine an average rate of change, and that connects back to a secant line. That would tell me how fast the particle is moving on average over an interval of time. But here comes the calculus. What if I want to know how fast an object is moving at a frozen moment of time? I would need the instant rate of change. So if I want to know the exact velocity of a particle at an instant of time, I would take the first derivative of position, which would give me velocity. So, fact that you must know, first derivative of position is velocity, and it is the instant velocity rather than the average velocity. Likewise, if we want to know how fast the velocity is changing, So we'll stay with red for velocity. The velocity function indicates velocity, and that would be measured in something like feet per second, miles per hour, meters per minute, and it tells, again, two things. It tells, number one, the direction a particle is moving, and that would be based on the sign. If the velocity is positive, the particle is moving to the right or up. Secondly, the velocity tells how fast the object is moving. The average acceleration, so from above we said the instant rate of change of the position function is velocity. This is instant rate of change when I take the derivative at specifically one point. All right, so now let's change colors again. I'll go with this brown color here. Now, if I want to know the average, look at the A word, average acceleration, average rate of change of velocity would be change in velocity over change in time. That would necessitate 2 points because we're looking at the average. And if we're doing a change in velocity, think about velocity. If we had an example where velocity is measured in feet per second, that is the numerator, time is measured in seconds, notice we're dividing feet per second, and that's where the feet per second squared come from. Another thing that you need to set to memory or hopefully understand and then memorize is that the first derivative, the instant rate of change of velocity, is acceleration, and that this would give me the instant acceleration at any moment of time. So therefore, the second derivative of position, so remember we said the first derivative back up here, we said the first derivative of position takes you to instant velocity. The second derivative, that means we took the first derivative and got to velocity, then we take the second derivative and that takes us to acceleration, and that would be the instant acceleration versus the average acceleration. As I said above, let's go back into red because we're talking about velocity. Velocity indicates two things. It tells you how fast the object is going, and it tells you the direction the object is moving in based on the sign. The sign of velocity reveals the direction. The number without a sign tells you how fast the object is moving. Now I'm going to warn you that the next thing is something that students often confuse. Speed is not equal to velocity. Speed is simply how fast an object is moving. It is the absolute value of velocity. Speed can only tell you how fast an object is moving, but it cannot tell you the direction it's moving in. Velocity has two quantities. Speed is only one quantity. Another thing that you have to understand is if you want to know how fast an object is moving, you take the absolute value of velocity. All right, let's look at a graph of three things that hopefully will help us to see some of these things. Consider the following example. A baseball player is holding a ball 5 feet off the ground. So that 5 feet off the ground, there is our initial, that is our initial position. Our initial position is 5 feet off the ground. He throws the ball into the air at 130 feet per second. There is my initial velocity. V sub 0 means initial, initial velocity. S sub 0 is initial height. The position function, as we talked about it on the other page, negative 16t squared plus, here's my 132t, that's my initial velocity, plus 5 is my initial height. This graph is already given right here, and notice it forms a parabola. Examine the graph. The graph indicates the position of the ball in the air at any time. So for example, let's say we freeze the ball right here at this particular time. Now that's going to be significant because we're going to follow this ball. We're going to get all the information that we can from every graph that we have below. So I'm going to insert a vertical line. There's my vertical line, and I'm going to follow that all the way down, and we can't see the acceleration, so I'll just leave it there for right now. So the first graph, the position, and I want to see something else because I can't, I'm going to make this a little bit bigger so I can see. So if you look here, let's make this a different color, maybe blue. If I come directly over, it looks like the object. So what I can tell from the position graph, I can tell you that when this ball is in the air, the only thing I can tell you from the position graph is that the ball is 190 feet in the air. All right, now let's go down and let's look and see, all right, if the ball is 100, let me write that down. So in my frozen moment of time, the ball is 190 feet in the air. Now let's see what happens with the velocity, because these four graphs are lined directly up under each other. I've already found the derivative of the position function. Notice if you use the power rule here and take the derivative, you get negative 32t, which is right here, plus 132. So this is my instant velocity of my frozen moment of time. All right, so let's follow the ball. Now the ball is not here, but I'm just going to mark this. The ball is 190 feet in the air. So what I can tell from velocity is two things. At this moment of time, let's draw that line over again. Let's do an insert. Let's get a horizontal line here. Insert shapes, horizontal line. So let's go directly over from here. Looks like I'm right in between. So I'll just call that 95 feet per second. So bear in mind the things that I just found out. The ball is 190 feet in the air, and at that particular time, and it looks to be about like 1.25 seconds, at about 1.25 seconds, the ball is 190 feet in the air, and the ball is traveling 95 feet. Did I say this was per second? I don't know if I indicated that. Yeah, it does say 95 feet per second. Notice that the sign of velocity, even though we don't write it, is positive. So that tells me the ball is moving upward. And we'll put the ball on the other side in just a minute to look at the difference. Let's follow the ball to the speed function. Now remember, speed is the absolute value of velocity. So I'm going to insert my shape again. I'm going to get a horizontal line. I'm going to go directly over. The ball is here. It actually should be the same. I'm just not hitting it at exactly the same mark. But notice that the speed is also 95 feet per second. I should not be surprised by that, because speed is actually how fast the ball is moving. All right, now when I follow the ball is still 190 feet in the air. It's going 95 feet per second. It's moving up. Edit, undo. All right, let's pull the thing down. Control it. There we go. So notice the derivative of the velocity function. Remember, it was negative 32t plus 132. The derivative of that is acceleration, which is negative 32 feet per second squared, which is the force of gravity, which makes sense because the gravity is operating on the object. So it really doesn't matter. See the horizontal line down here? That's my acceleration at negative 32 feet per second squared. So when the object is 195 feet in the air, it's traveling 95 feet per second, and the acceleration at that time is 32 feet per second squared. All right, let's place the ball on the other side. and we'll do a different color ball. We had a blue ball, so now we will do I guess a pink ball, I don't know. Now notice that the ball, if I can hit it correctly, is going to be 190 feet in the air once again. Let's draw a vertical line all the way down and follow the pathway. Mainly I just want to look at the velocity. So there's my vertical line. Let's do this. That'll allow me to draw the line all the way down. There we go. Okay, so what I want you to notice, let's just believe that I hit the mark correctly. I'll make this a little bigger again for you. So let's believe that I hit the mark again correctly and that the pink ball is still, let's find my mouse here, there you are. The pink ball is still 190 feet in the air, but this is what I want you to pay attention to. Now we're down the ball, the velocity is indicated down here. Notice that it's still going to be 95 feet per second, but it's negative 95 feet per second. The negative indicates that the ball is falling, and you can see that because on this side the ball is going down. That's why velocity has a lot of power, because it can tell you two things. The sign of velocity tells you the direction the object is moving, and the number tells you how fast. But on the speed graph, even though I didn't hit it very well, bad me, I should slide that over a little bit. Let's do that. The speed is still the same, even though it doesn't look like it, but that's really me not hitting exactly the mark on the other side, so sorry about that. All right, let's learn some fun facts in physics. So fact number one, let's talk about, edit undo, let's go ahead and lock that up. Locked, all right. Let's move this little guy right here. What is the difference between the two D words? Now this is really important. We have distance traveled and we have displacement. So I'm going to use our happy little math guy here to try to help you to understand the difference between distance and displacement. Sometimes distance and displacements can be the same and sometimes they're different. So let's assume, let's move our little stick figure here. If I can get him to move, come on, I believe in you. All right, there he is. All right, so let's assume that our stick figure is starting, his initial location is at 1 on the number line. That's the starting location. And our little stick figure decides to move 1 unit, 2 units, 3 units, 4 units, 5 units. So now the current position of the stick figure, terminal position, where the stick figure stopped, is at 6. The stick figure started at 1. 6 minus 1 is 5 units traveled. So remember, our friend started at 1, traveled to 6. So in this case, the displacement and the distance traveled are exactly the same. Displacement means that stick figure is 5 units to the right of where it started. It started at 1, it is now at 6, so it has been displaced 5 units from where it started and also traveled 5 units to the right. So in this case, distance and displacement are exactly the same. All right, so let's get rid of that and do a reset. Now this time let's start our stick figure again at 1, and let's mark where he is starting. So now he's going to start again at 1, so we'll mark it right there. And this time he travels, edit undo. He travels 1, 2, 3, 4, so he's traveled 4 units to the right, bear that in mind, but then he decides to turn around because he forgot something, so he's traveled, remember, 4 units. Let's do that again. 1, 2, 3, 4, but he turns around and goes back 3 units. 5, 6, 7. Now look where he landed. Let's mark that in blue. So he landed right here at the 2. So his displacement, the way that we're going to find displacement is this. His terminal position is 2, terminal, minus his initial position is 1. 2 minus 1 is 1. So his displacement is positive 1, meaning he is 1 unit to the right of where he started. 1 unit to the right of where he started. But remember, the distance traveled was 7 units. Because he went 4 units to the right, 3 units to the left, so the distance and the displacement in this particular case are not the same. So distance and displacement are sometimes the same, assuming the particle is traveling, definitely when the particle travels, or in this case, our little happy math guy, when he travels to the right, distance and displacement will be the same. But when we change directions, we run into distance and displacement not equaling to each other. All right, let's do one more example to take a look at that. So we have reset our little happy math guy. For whatever reason, he likes to start at the number 1. Partially because I don't want you to assume that all objects begin at 0. So let's mark his starting place. So he is starting at 1. And let's see how he travels now. So this time he's going to travel. Come on, happy math guy. There you go. Come on. Click, click. All right, there he is. So he's at 1. So he's going to travel 1, 2, 3 to the right. So far, I'm going to write that number over here so I don't forget. So far, he has traveled 3 to the right. Okay, now he decides that he's going to change direction, and he's going to travel 1, 2, 3, 4, 5, 6, 7 to the left. So now notice that his total distance traveled, he went 7 to the left, he has traveled a total of 10 units. That is his distance. Now let's mark his landing spot. His landing spot is -3. So that is his terminal, and this was his initial. So to get his displacement, we're going to take terminal minus initial. Terminal landing spot was -3. Initial spot was 1. 3 minus 1 is -4. That means that happy math guy is 4 units to the left of where he began. He landed at displaced. That is his displacement. All right, let's see what else it says under our little screen here. Let's move happy math guy out of the way. There you are. Distance is a linear measure. It's measured in feet, miles, etc. It's the number of units traversed by the object. Distance traveled is not a factor, so it doesn't matter which way you're traveling. You just keep counting it up as a total. Distance is always positive. Distance is a linear measure of the net units traversed by the object. Distance traveled is a factor in displacement. The direction you travel in affects your displacement. I showed that in the example. Displacement is often indicated as change in position. Displacement is terminal position minus initial position. Displacement is relative to the starting point. The starting point is not assumed to be 0. Displacement can be negative, whereas total distance traveled cannot be. All All right, how can velocity be used to determine the times which a particle changed direction? We might have to bring our happy math guy back in to help us out with that in just a second, so let's do this. Things to know about velocity. Velocity is a vector quantity that indicates speed and direction. I already talked about that. The sign of velocity. I'm trying to get my happy math guy to come back. There he is. Come on down here, buddy. There you go. So the sign of velocity indicates the direction the particle's moving, and the number is how fast a particle is traveling. The sign of velocity indicates direction. Speed is the absolute value of velocity. And now here's the important thing. One of the important things, sorry. A particle changes direction when the velocity changes sign either from positive to negative. Particle changes direction. So for example, let's bring happy math guy back up. Come on, happy math guy, come on. There you go. All right, so let's say happy math guy starts at 1. And he's traveling first to the right. So he's going to go to the right. I don't know how far he's going to go, but he's going to go. And he's moving at, I don't know, 3 feet per second. So he starts moving. He's moving to the right. And he's moving at 3 feet per second. Because he's moving to the right, his velocity is positive. But then he gets tired and decides he wants to go back where he was going before. So now he's going to turn around, and when he's traveling to the left, his velocity is now negative. So we would say, let's say he's moving slower at negative 2 feet per second. That means he's moving to the left, and his speed is 2 feet per second. So velocity indicates two quantities, speed and direction. Sorry, I'm just trying to lock this down. All right, so let's just do this. Let's see, let's go down to the last part, and then we're going to do an example. The relationship between speed and velocity. Give me a second here. What is the relationship between speed and velocity? How are they alike and how are they different? Velocity indicates two pieces of information. Speed indicates one piece of information. Speed is only how fast the object is going. Speed is not speed is not velocity, and speed is not acceleration. All right, let's do an example together. Then I'm going to tell you to stop the video and do a second example. This is going to be a calculator-friendly activity. I'm going to make that a little bit bigger, and I'll show you how some of this works. All right, suppose Mr. Jernigan drops Justin from a height of 100 feet. So the 100 feet is going to be the initial position. And of course, he's dropping Justin onto a very soft ground because he doesn't want Justin to get hurt. And because he is simply dropping Justin, we may, in this case, assume that the initial velocity is 0, just holding him in the air, letting his legs dangle, and then he lets him go with no force. Letter A, determine his distance from the ground at t equal to 1, t equal to 1.1, t equal to 1.5, and t equal to 2. So bring out your graphing calculator and let's create, first of all, let me write my function. So our position function would be negative 16t squared. We have no initial velocity, and we have an initial height of 100 feet. That is my position function. So if I want to determine his position, and I'm simply going to use a calculator for efficiency, I already have my function typed into my graphing calculator. It's right there. negative 16t squared plus 100. I have some other functions that we're going to use on the second example already typed in. So you may want to stop for a second and at least get this into your calculator so you can see efficient ways to use your calculator. So to determine his distance from the ground at 1 second, 1.1, 1.5. I think the most efficient way to do that, noticing that my y1 is already in my calculator, I'm going to go to the home screen. I'm going to do my shortcuts. I'm going to do alpha F4. I'm going to select y1, and I want to know the position at 1 second. So that's going to be 84. So S of 1 is 84. Then I'll do the same thing, except the way that I will do it is I will do second enter, which brings back the y of 1, and I'm just going to go in here and make it 1.1, close, enter, 80.64. So position at 1.1 is 80.64. And then I'm going to come back and do 1.5. So I'm going to do second enter to bring that back. 1.5, 64. So position at 1.5 is 64. And then lastly, position second enter, position at 2, and then I'm going to get rid of that stuff, delete, enter, is 36. So position at 2 is 36. All right, now the next thing we're going to do is to find the average. Look at your keywords. Average means I need 2 points. So we're finding the average rate of change, which is the average velocity. So that would be his position at 2 minus position at 1. There's my difference quotient over 2 minus 1. I have those numbers already here, so I'm just going to retype them in. So position at 2 minus position at 1. So we have 36. Let's put that in parentheses. 36 minus 84, close parenthesis, divided by 2 minus 1. Well, we don't really have to do that, but that's what we wrote. So on average, Justin is moving downward because I see a negative. He's moving at a speed of 48 feet per second. His velocity is negative 48 feet per second, meaning he's going downward, but his speed, how fast he's moving, is 48 feet per second. Now, I'm not going to do the next two. I'm not going to do 1 to 1.5 and 1 to 1.1. I encourage you to do that because what you should notice is that I'm decreasing the intervals of time. We went from 1 to 2, 1 to 1.5, 1 to 1.1. So we are decreasing the distance between the 2 points so that if you calculate those, you'll see, because look at the next question. It says what, well, let's answer the next question. What does his average rate of change represent? His average rate of change is Justin's average velocity. It's his average rate of change of position, because we did change in position over change in time, like from our notes on the first page. But it is his average rate of change of position, which is his average velocity. Now the next question says, all right, let's move from average to instant rate of change. So now, because we have the word instant, we want the derivative of the position function. So we want s prime of t, which will give us v of t. So I'm using the power rule. Here's my position function back up here. So the derivative of negative 16t squared is negative 32t, and the derivative of 100 is just 0. So my velocity at 1 second would be 1 times negative 32, which is negative 32. That is his instant velocity, meaning that at 1 second, Justin is moving downward because of the negative. He's moving at exactly 32 feet per second. His velocity at 3 seconds would be v of 3, substituted into the velocity function, which would give me negative 96 feet per second, meaning he is still going downward, and he's moving at 96 feet per second. I think there's one more question here. Nope, that's it for that. Oh, yes, there is. At what time does Justin hit the ground? Well, you can answer this out loud. Nobody can hear you, though. I can't hear you. At what time does Justin hit the ground? Hit the ground. Is hit the ground position or is hit the ground velocity? Hit the ground is position. In other words, it's saying, when is Justin's position equal to 0? So on my calculator, I'm going to figure out, I'm going to make the calculator do it for me, when is the position equal to 0? I already have the position function in my calculator, and I already have 0 in my calculator as well. So I'm going to do a Zoom 6 window to make my graph. Now I can open the window more to actually see all of the parabola, but I know the number that I'm looking for is right here. And again, you can stop the video, take your time, practice the calculator yourself, type everything in. But the number that I need is right here because nothing was really happening back here at negative time. So to get my point of intersection, I'm going to do a second calc, number 5, which is a point of intersection. The cursor, even though I can't see the cursor, it's at 100. It's at the y-intercept. I'm going to move that a couple of ticks to the right. So over here, I'm going to arrow to the right, arrow to the right, arrow. Okay, so I'm going to stop right there, even though I still can't see it in the window. Enter, enter, enter. And I can see that Justin hits the ground at 2.5 seconds. So that's when Justin hits the ground. Now what I'd like for you to do if you're in my class is to stop the video and do problem number 2 and then resume it to see if you get the same things I get. I'm going to continue on into problem 2, so now stop the video, do it, and then check your work and see if we agree. So for problem number 2, our class takes a field trip on the calculus bus. We are flying at an altitude of 7,000 feet. That is our initial position, S sub 0. Our mission is to share our calculus knowledge with the needy math students throughout the United States. Suddenly we spot a group of children who know nothing of calculus, so we throw a set of spiral-bound note cards along with a one-way ticket to get on the bus towards them at a velocity of negative 150 feet per second. That is our initial velocity. So the position function would be, I'm going to not go as slow this time because hopefully you've already tried this problem. So the position function, S of t, is negative 16t squared plus, actually no, it's minus because we're throwing them downward. So negative 150t, and we are 7,000 feet in the air. Determine the function that represents the, look at that word, the means instant velocity. The is instant velocity. So I would, to get the, or the instant velocity, I take the first derivative of position which will give me the velocity function. Using the power rule, I get negative 32t minus 150. And that formula will tell me how fast the note cards are moving at any time t. Next question. What is the acceleration? The acceleration means instant acceleration. So I would take the second derivative of position, which is the first derivative of velocity. And if I use the power rule on my velocity function, I get negative 32. The derivative of negative 150 is 0. These are my instant velocity and instant. Oh, by the way, I didn't put A of t. I should have. That would be A of t. Letter D. How far are the cards from the Earth at 5 seconds? That would be position at 5, which would come off of your calculator. The position at 5 seconds is 5,850 feet in the air. Next question. Determine the velocity after 10 seconds. That would be v of 10, because it says the. That would be 10 seconds substituted into the velocity function. That would give me negative 310 feet per second. That means that the note cards are still moving downward because we have a negative rate, and they're moving at 310 feet per second. Letter F, calculate the average velocity. Be careful, look at your keywords. Average is your Algebra 1 idea, so average rate of change. So that would be position at 10 minus position at 5, again off of your calculator. Let me slide this down just a little bit. Don't have much room here. I can do it. Divided by 10 minus 5, again straight off your calculator. That should give you negative 390 feet per second. So notice the difference between average and instant. Average requires 2 points. Instant is at a frozen moment of time. At what time do the cards hit the ground? So for that one, I'm going to come back in here to y equal to. I'm going to turn off my first equation. For my first problem, I'm going to turn on my second equation. I want to know when the note cards hit the ground, so I'm going to start with a Zoom 6 window. I notice that nothing from the parabola appears, but remember we were way high in the air, so I'm going to go to the window. I was starting at 7,000, so maybe I'll do the Y max at 10,000. And my Y scale may be counting by, I don't know, 50. I'll just play with it. And then I'm going to open the X max to, let's say, I'll play around with it, let's say 50, and I'll count by tens, and let's see what that does. When you're playing with the window, you're playing with the window, literally. Oh, I see it, nice. All right, I wanted to know when the object is going to hit the ground, so I'm going to do a second calc 5. Be careful. Look right here. It shows you that currently the cursor is on the second function, which is fine. We want to know where the black curve intersects the red curve, so that's okay. I'll press enter. It's on the second curve. I look right here, especially when I have multiple functions in there. I do want it on that second curve. Enter, enter, and the time is 16.748, either rounded or truncate, 16.748. So, come on, where are you? 16.748. And then on my calculator, I would substitute that time into the velocity function. You should get, if I calculated it correctly, negative 600, whoa, that's fast, negative 685.930 feet per second. And since the acceleration is constant at negative 32 feet per second, the acceleration is going to be just that, negative 32 feet per second squared. And lastly, at what time is the velocity negative 470? So I'm going to go back into y equal to. I'm going to turn off my 0. I'm going to put in, I want to know when velocity, so I'm going to turn off position. I'm going to turn on velocity. I'm going to go down to negative 470. I want to graph the horizontal line because I want to know when is velocity negative 470. So that would be v of t equal to negative 470. I'm going to change my y minimum to, let's just say, negative 1,000. Graph. And I can see my line and my velocity and my negative 470. So second calc, 5, enter, enter, enter. And that happens at 19.375 seconds. So, hope this video has been helpful. We will talk a little bit more about this in class tomorrow.